All right, we've just got a few more things to tie up on this chapter. We just finished talking about orthonormality, which explains that the orthogonality portion explains that if two eigenfunctions of a particular operator are multiplied by one another and that function is integrated over all space, we will get zero. That means those functions are orthogonal to one another. But that if a function is multiplied by itself, if we take the square of a wave function, or really multiplied by its complex conjugate, and integrate that over all space, we will need to get 1 so that the function relates to probability in the proper way. Additionally, we want to talk about completeness. Any well-behaved function can be expanded in the eigenfunctions of any quantum mechanical operator that is of interest to us. So what we're saying is a particular wave function may not be an eigenfunction of that operator, but it can be written as a sum of functions that are eigenfunctions of the operator, and we would need a complete set of that, and for some functions that might be an infinite number of functions we would have to add together to get the quantum mechanical function we are looking for. So for example, and if you can take a look at this in the end of chapter 2, and I'll have some neat videos on the last slide here to take a look at this. The sawtooth function can be approximated as the sum of sine and cosine functions, with approximation improving as the number of terms in the sum becomes larger. So the sawtooth function itself would not necessarily be a well-behaved eigenfunction of any particular operator, but each sine and cosine are. And this method is going to become extremely useful to us, this thought process, later in the course when we have to approximate wave functions that can't be solved directly. And so when we use the term basis set, this is what we mean. These functions that we'll be adding together, these sines and cosines that we'll be using to add up to the sawtooth function, will serve as a basis set to approximate the sawtooth function. Here's what we mean. The sawtooth function is in black here, what we want to approximate, the function we're going for. And what we're doing is we're taking these sine and cosine type waves at different amplitudes, different sizes, and adding them together. And as we add up all their amplitudes, what we're doing on this bottom graph is showing the functions we're adding together separately. And then on the top graph, we're showing the functions, the result of having added them together. And by the time we get to 15 different terms in this summation, we have a pretty good approximation of a sawtooth function. And that's going to happen to us for any molecular system where we have 2 or more electrons. Even an atomic system where we have 2 or more electrons, we will not be able to get an exact solution, an exact wave function for the system, but we'll be able to approximate it as a sum of eigenfunctions. And so we're going to pick up with this in the next chapter and start to develop some more ideas about this.